to the other side. So zt moved over here, and all the poses moved over here. So we have p of zt given all the poses times the what is this? The poses. That should be no. Times all the poses. The only thing I did here, I just factorized it. And all the poses can be factorized in the current pose, given the previous pose, and the belief about all previous poses. So it's like p of x1 to t is p of xt given xt minus 1 times p of x1 to t minus 1. Right? This is just standard factorization. And here, using the Markov assumption, otherwise I would have 1 to t minus 1 here. This is just standard factorization, and this is exactly what is done over here. So this term, the second part of the base rule was all poses from x1 to t, which is here split up in xt and all the previous poses. And I have my normalizing term, of course, over here from base rule. That's it, what happened so far. And now you can see we can easily simplify this. These two guys are exactly the same, right? And these two guys are exactly the same. So perfect, we can get rid of all of them. And so the only thing which remains is my normalization constant, which needs to make sure that the weights of all samples sum up to 1. And this term over here. So the likelihood of the current observation given all the poses and the past observations. Okay? Okay, let's take this term and take it a step further. What I can do in here is I can integrate over the position of the observed landmark, like the marginalization step rule from which this. So I introduce the position of the landmark j, so the landmark that I observed. I get this term over here. So here mj, here sits mj is given, and then mj given all the rest. Right? Okay. Now I can look to this to these terms and say, okay, given I know the current pose of the system and given I know where the landmark is, I can get rid of all previous poses and all previous observations. So it's exactly the same assumption we did in whatever Monte Carlo localization and all our models is. Given we know the state, so given we know where the landmark is and given we know where the robot is, we can compute the likelihood of an observation. So this term simplifies to exactly this equation over here. And the second term remains as it is. The only difference is here I get rid of the xt because let's say if I only have observations up to t minus 1, I don't care about where the robot was in the future in order to estimate the location of a landmark. So just if I know where the robot is in the future, it doesn't help me to estimate the position of the landmark. Also a step we have done in the past quite often. Okay, so what do we have in here? What we have in here, what is this? Which problem is this one? Estimating the location of a landmark, single landmark, given our observations and given the poses. Mapping with known poses. So this is our 2x2 EKF, which we can use to compute that. So it's a Gaussian, which we know how to estimate. What we have here is the likelihood of an observation given we know the poses and given we know the landmark location. Again, we go back to the EKF, how we done that in the EKF. We know that's all quite easy. And under the assumption that this is kind of a Gaussian, that we use a Gaussian model, this is the likelihood of the current observation given the predicted observation and the uncertainty of that observation. Exactly the same as in the EKF, right? Where we used this to kind of trade off for computing the Kalman gain. And the second thing, what is down here is just the estimate of the location of the landmark given the terms from our what we computed with the EKF, our EKF estimate. And as a result of that, I can combine that as the measurement covariance matrix Q, which is given by the previous estimate. This is just the Jacobian of the observation, plus the measurement noise. So, if it's okay, this is the uncertainty of this belief up here. This results in a Gaussian distribution where this Q is exactly this measurement covariance, and here the predicted observation. The only thing I have in here says this is an approximation, it's not exact. And the reason why this is not exact is because there's a linearization involved from. So we again have to linearize my observation function if I do it in that way, similar to the EKF. So as a result, the importance weight can be computed by evaluating the Gaussian distribution and comparing what's the difference between the current observation and the predicted observation, given the expected uncertainty of that belief, which is given by how certain am I about the location of the landmark and plus the uncertainty of my sensor. So this perfectly fits with the intuition I said before in the beginning today. I say the weight tells me how consistent is the map that the particle built with what the robot currently sees. This is exactly what's written in here. This is what the robot currently sees. This is what the particle estimated. And in here is also encoded the sensor noise and the uncertainty of the estimate of that particle. So the weight tells me how consistent is the world representation that the individual sample generated with what the robot physically perceives. And the closer the expected observation is with the observations the system obtained in reality, the higher the weight. So the better the model that this particle built, and the better the pose estimate of that particle in turn. Okay? And this is the reason why in this algorithm we have this line over here on how to compute the weight. That's it. That was all the black magic involved in FastLab. So to summarize, the key design decisions have been we take the proposal as a proposal distribution my odometry motion model. As a result of that, of this design choice, I need to compute the weights according to this distribution. And as the landmarks are independent of each other, given I know where the system was during the mapping process, I can use small, tiny 2x2 Kalman filters, or extended Kalman filters, to represent the location of the individual features for every single particle. And this is this EKF update step, which I then do. And this is kind of the whole magic of basic FastLab 1.0. Is there any question I can answer you right now from that? Okay.
Maybe.
Yeah, sure.
How do you get rid of the integral? I didn't get.
So what you see in here is it's a mixture between two terms. So you have in the end it's a convolution of a Gaussian distribution where you have an estimate and you have the uncertainty of the observation. And this is a convolution of the Gaussian distribution with the Gaussian, which is Gaussian again, and that's the way how this results in that. So that's kind of the reason why you can show that under the assumption that these two guys are Gaussian, the result is a Gaussian again. But very valid question. Okay, so now let's look into one thing which we ignored so far, but this is, or for the EKF at least, we assumed we have this data association. So we assumed we know the data association, this C, correspondence variable C was given. So we knew which observation corresponds to which landmark. How to actually do that in practice? And if you see this example over here, let's say This is where the robot